Thanks for the introduction. Hello everyone, I'm Kevin Huguenot. I'm going to present some work about checksums today. It's a joint work with a number of colleagues from the University of Lausanne, but also Swiss Data Science Center at PFL and from Google. All right, so today I'm going to talk about checksums and how they're used for integrity of web downloads. So I would like to clarify a bit the situation and maybe run a couple of questions by you. So essentially by checksums for web download, I'm talking about these not so short hexadecimal strings that you may see on some download pages on some websites. So I would like to ask you a couple of questions, starting with a basic one. So who has VLC installed on its computer? Okay. Who downloaded it directly from the website? Okay. So who noticed the checksum? Okay. Less and less. Who checked it? Yeah, that's right. Okay. So for the last question, I will have to answer it myself. So how did you check it? Okay. When I do, I don't often do it, but when I do, I check only the beginning and the end. And this is what we're going to talk about today. All right, let me clarify the setting here and the threat model. So essentially, there are multiple ways to obtain programs from the internet. Most people, obtain the program that they put on their computer from the internet. There are several sources. The first one is app stores. Typically on Windows, you have like the Windows Store and the Mac App Stores on Mac. Another way is those repositories like Brew for Mac or Aptitude on Linux. And the last way that I will focus on today is when you download directly the software from the website of the, let's say, the vendor or the developers. All right, so for, let's say, efficiency and for performance reasons, very often the download web page, the front end is on a given server, but the files themselves are hosted on CDNs, typically Akamai or like content delivery network. And the threat we are considering here is the case where the file hosted on this external platform could be corrupted. So one way for the, let's say, the website administrator, the administrator of the front end, to allow the user to perform some integrity verification, being able to detect whether the file has been tampered with or not, is essentially to use checksums. Again, checksums is those hexadecimal string that you can find here. So the way it works is that those checksums are essentially just the digest produced by hash function, cryptographic hash function, in such a way that if the file is tampered with, it is difficult for an adversary to produce a tampered version of the file that matches actually the checksum, allowing the user, the visitors, to essentially verify the integrity of the file they just downloaded. All right, so more specifically, how does this checksum verification works? So first, the user has to download the file from in their browser. Then they have to fire up a terminal window, type some barbaric command. Then they get the checksum on the web page, the checksum on the terminal, and they have to look on the left, look on the right, look on the left, look on the right, and detect if there is a mismatch. What year is it exactly? I mean, we're talking about machine learning for security and so on. And in 2018, we're still asking people to essentially compare those 64-digit hexadecimal string. Okay, that's insane. So essentially, what we did in this work is look at this checksum thing from different angles and try to answer a number of research questions. The first one is: do websites use those checksums, and what are the common practice with those checksums? Do internet users use checksums, and how often? And the third one is: how effective and usable are checksums? Well, usable, I kind of already sold the answer here, but spoiler alert, the last question is some of these answers are negative, so can we do better? Of course we can, and I'm going to talk about that. All right, in this work, we also produced a number of artifacts. Essentially, we proposed modification to web standards. I will describe this in more details later. And we created tools to generate and verify checksums in a, let's say, automated fashion. So to answer those research questions, we used a number of instruments. The first one was a survey of internet users at large scale to answer not the first, but the second question related to how internet users do interact with checksums. So the setup was the following. The survey was run in April 2018. We surveyed 2,000 internet users. And for that, we relied on SSI, one of the providers that was mentioned in the previous presentation, to obtain a representative sample of the US population. So I'm not going to go into the details of the questionnaire. I will just distill a number of results here. So essentially, around 58% of the surveyed participants do download programs from vendor or developer website, which means that they might be exposed to the threat that I just mentioned, which is essentially the case where file hosted on CDN are corrupted. And by the way, this happens. It happened to the transmission BitTorrent client a couple of years ago. Same for one of the Linux distribution. I think it was Mint. So these kind of attacks do occur. The second important number here is that 23% of our participants remembered having seen checksums on website. So it's remembered. So the number of people actually exposed to those checksums might be even higher than that. And the last question, which is probably the last result, which is probably the most interesting, is essentially we gave a number of possible explanation of what checksums are for, and we asked the participants to click on the correct one. There was 6 options plus the I don't know option, and only 5.2% of the participants clicked on the correct answer, which was essentially verify the integrity of checksums. So again, the conclusions here are that users are exposed to the threat. That's something. And the second thing is that people need education or at least tools. I mean, they have no idea what those checksums are for. I mean, some of the participants even answered like, when I see a checksum on a website, I just exit the website and pick another one because it sounds fishy, so, which kind of defeats the purpose of the whole thing. All right. In order to assess the, let's say, the current practice with the use of checksums on the website, we conducted another survey, a survey of website, this time small scale. The setup was again run in April 2018, and what we did here, we're not claiming that the sample that we analyzed is big. I wrote it here; it's small, and also it's not representative. We just picked a number of websites and checked what were the current practices. So what we did is essentially we compiled a number of lists that you can find online that give you the 10 most useful open source software or the software that you need to have on your computer and so on. And we surveyed the download web page of those websites and checked the current practices according to the following criteria. Whether they use the same origin or not. Essentially, it means whether the binary is on the same on the same server as the website. It doesn't hurt security, but it means that it doesn't make a lot of sense, because if an attacker can break in to the server, it can modify both the file and the checksum. We looked at whether they used secure connection, essentially HTTPS, which hash function they used, knowing that some hash functions such as MD5 and SHA-1 are considered insecure as of today. And most importantly, whether they had instructions to essentially guide their visitors into the verification process. So I put the raw result here. We analyzed 20 websites or so. We analyzed further later, but they are not in this table. So I guess you probably know those most of this software. Typically, most importantly, there are 2 that are particularly interesting. It's GNU-PG and Tor, which are like security software. So it makes a lot of sense to actually look at those software, because they might even be used by a population at risk that really don't want to get a corrupted binary of these files. And if we look now at the different column, the conclusion that we can draw here is that actually a large proportion of this software, of this download web page, do use insecure hash function or checksum generic from this function, typically MD5 and SHA-1 here. And that actually only a small fraction, less than half, I think, of this website include instruction. That is, they just throw this checksum on the web page and tell the visitor, deal with it. I mean, you probably know how to use that. They don't, but they think they do. All right. So again, from this data, the goal is not to assess the prevalence of checksums or even like how frequent is a given behavior. It's just to get an idea of the typical mistake that can be made when using checksums. And the conclusion here is that there is like often improper or insecure use of checksums, and definitely a lack of instruction, which hurts the usability or even like the understanding of the visitors. All right, the last instrument we used to assess the effectiveness and the usability of checksums is an in situ experiment, small scale. We had 40 users. It was run in April 2018 as well. The experiment was around 50 minutes per participant, and we paid them 20 Swiss francs, which is pretty much equivalent to $20 US. So we recruited participants on the campus, the PFL campus and the University of Lausanne campus. We got a total of 40 participants. 40% of them were female, and we had like it was roughly balanced in terms of operating systems. So there was first a screener that allowed us to essentially balance, try to find a balance between the different operating system, gender, majors, and a priori knowledge of checksums. So just a couple of statistics here about our sample. 83% of the participants reported downloading programs from vendor developer website, which is again a sign that the participants a large portion of the participants that we had were essentially exposed to the threat, and only 30% of them knew about checksums. Here, the point is just to see whether there is a difference between users who know checksum and those who don't in the experiment. So the procedure was as follows in this experiment. So the goal was to remind you the goal was to assess the usability of checksums. So we had a computer equipped with eye tracker. I'm going to give details on that. The user was supposed to use them. They had a leaflet with the instruction, the steps that they were supposed to follow in this experiment. And at the end, we had an exit questionnaire. So the computer, essentially the eye tracker, is a small device that you put on top at the bottom of the monitor, and that records essentially where participants look at. It's a good way to essentially capture objective metrics of let's say the way people interact with the monitor. And the two metrics that we measured here are essentially the number of fixations and the dwelling time. That's what we use. As for the instruction, what we asked the participants to do for 4 different software, essentially Handbrake, VLC, Transmission, and Android Studio, was to download the file, to compute the checksum by using the terminal window, by typing a command that we provided them with in the instruction, then to check the checksum, and like some useless instruction at the end, essentially to extract and note down some information about the program, typically the version number or some information that could be found in the about box. So the goal of this last step is just to make sure that the participants don't put too much focus on the verification of checksums, and essentially we didn't want them to realize that the real purpose of the experiment was to observe their checksum behavior. One of the checksum of the third program, transmission, essentially was incorrect, but it was what we call a pre-image, partial pre-image attack, in the sense that the first 10 digits and the last 10 digits of the checksum were correct. So the underlying hypothesis here is that users can be fooled, and we wanted to test that through our in situ experiment. And in the end, we had an exit questionnaire. I will not comment too much on that, to receive feedback and assess the understanding of the about checksum from the participants. So the general window arrangement in on the laptop that the participants were using was like that. They had like a browser window here on the left with a number of tabs open for the different programs to download. They had like the download folder here and the terminal window here. They were not allowed to move the windows, otherwise it's kind of mess up with our eye tracking result. So the result of the eye tracking are something like that. The eye tracking software allows us to select time interval and to get a heat map of user attention on the different portion of the screen. So what we can see on the left here is that this is the case of a successful verification. This was for transmission, yes, transmissions here. And we see that there is a huge emphasis, a big emphasis at the beginning of the string, but still they look all over the checksum on the left case. On the right case, they just look at the beginning and the end. And on the left case, it was a case where they didn't detect the mismatch. All right, so the results of our experiments are as follows. 38% of the participants did not detect the mismatch for transmission, okay? We then performed some advanced analysis to see if there is any correlation between the detection and the number of fixation and time. And surprisingly, this is correlated in the sense that people who paid more attention and had a higher number of fixation or dwelling time on the checksums were more likely to detect the mismatch. However, we're quite surprised to see that the detection rate does not correlate with prior knowledge on checksum, in the sense that users that knew checksum before the experiment were not better at detecting the mismatch. One reason for that is that people who know how checksum work, in their mindset, they know that accidental changes of the file would completely shuffle the checksum, and therefore they just check at the beginning. If the first character matched, then they're good to go. And finally, what we observed, which was a bit different from our working hypothesis, is that essentially people focus at the beginning of the checksum. They don't even look at the end. So we do, I mean, like as experimental, we thought that they would look at the beginning and the end. And in fact, they look only at the beginning. So to measure that, what we did is we split the checksums in 4 areas of interest. and then we measured the fixation time and dwelling time in those 4 different areas of interest. And what you see on the graph at the right here is that the attention and the dwelling time decreases from the first to the last, which means that they pay more attention at the beginning of the checksums. All right, so the conclusion here is that the verification process is error-prone, unsurprisingly. I mean, 40%, almost 40% got fooled here, and that attacks, partial pre-image attack, that is attacks where the beginning and the end match, can succeed. So there is obviously a need for automatic solution here. So we came up with a number of solutions, but let's be clear, there is a solution that almost exists. Okay, so there's this thing called sub-resource integrity that was proposed by the W3C, the World Wide Web Consortium, in 2016, that essentially allows, in the HTML code of a page, allows the developer to essentially include an integrity attribute in the script and link elements, which essentially refer to JavaScript external files and CSS files. So you can essentially, with SRI, you can essentially integrate this integrity field, which specifies exactly a checksum, which means that if the user agent detects a mismatch between the integrity field that was declared and the actual checksum of the script file that is downloaded, then the file is just not loaded. So essentially, what we propose here is pretty simple. It's essentially to extend SRI to A element, A being here links that allow you to download a file. Not to be confused with the link element that actually refers to CSS elements. Okay, so we are currently, there is an ongoing discussion for a version 2 of SRI in which we are involved. If you're interested, you can follow, look at this link here. And the goal is to essentially extend SRI not only to A element, but also to image element, media element, and so on, just to make sure that when you point to some remote content, you point to a specific version. If the file name is modified, then you don't want the link to work anymore. All right, we also came up with a browser extension, which is available on GitHub. The link is in the file, that automatically extract checksum from A elements, the integrity attribute, but not only, because let's face it, no website on the web now uses the integrity element for the integrity attribute for A elements, but our extension also extracts the checksum from the text of the web page. Okay, it intercepts the downloads, and after the file is downloaded, it computes the checksum, compares it to the checksum that was extracted from the web page, display a message to the user, and highlight the checksum. I think I don't have the time for the demo, but there is a link in the paper, again, to a video that shows it. Here you can see just a small screenshot of it. So it's on the download web page. So essentially, when you click on the download button, it shows up this pop-up with like an animation saying, oh, file being downloaded, checksum being computed. And in the end, there is a message. Here the message says that essentially the checksum matches, the checksum of the file matches the checksum on the web page. And it highlights here the checksum on the web page just to show people what checksums are, and so that they can identify it on the web page. All right. Yeah, I will skip the demo. And finally, the last artifact that we produced is an extension for WordPress, knowing that WordPress essentially serves more than 1/3 of the web page on the web. An extension for this content management system to essentially automatically generate the checksum. That is, every time on WordPress that you include a link to an external file, the extension here computes the checksum of the file and integrates it into the integrity field of the link put in the web page. All right, so that's it for this work. A couple of conclusion and perspective here. Essentially, we started this work because we're really surprised that these checksums that you see on the web page and that we expect nobody to use are still present today in 2018, and it was never studied. Yet, it seems that it is an important part of the web security environment, and very popular websites keep using them. VLC again, Bitcoin, Ethereum, Google's web page, and so on. So here we did we used several instruments to look at the problem from different perspectives. But it definitely requires more in-depth analysis. Typically, what we did on a small scale, looking at a small number of websites and looking at the current practices, is not enough. We really believe that. Oh, time's up. Is that it?
Sorry, we got about 1 minute left.
1 minute. Okay, good. there's a more in-depth analysis to be done here to look at the prevalence of checksums and the current practices. And also, we really believe that probably the solution is through standardization and ultimately implementation in the browsers. But even if we start implementing that, I really feel that there are like a number of problems that will arise, exactly like for typically HTTPS certification errors. What if there is a mismatch? How do you communicate that to the user? How do you make user understand what's going on in the background and so on? That's typically something we want to do. And I have like one last point, and I would be really interested to talk to people if there are some people that are in touch with, let's say, population at risks, typically journalists, activists, and so on. I would be really interested to know how people in this population react to this kind of thing. Do they, if even them don't check checksums, then I don't really know what to do. But I would be very interested to talk to these guys. And one last note: everything I presented about checksums applies to PGP signature verification as well, and the extension works also with PGP verifications. I'm done.
We have a few minutes for questions. If anyone would like to ask?
Thank you. It is a very nice talk. So anyway, my name is Duan Kim from the Maryland. So I have a question: is that how many software used in the lab study is our code sign? Because code sign is guaranteed the integrity of software. So if the software is code sign, so we don't need to check the checksum, right?
Well, not really. I think it addresses a different problem. So essentially, if the code is signed, it just means that the binary that you receive has been produced by a person associated to a given account, right? But how do you know that this account corresponds to the actual developer that you expect? What I mean is that you could very well have a corrupted version of I don't know, like an Acrobat Reader that is signed with a valid account, but this account does not correspond to Adobe.
No, actually, publishers assign the software. So the software and then the big code sign PKI is like PKI is guaranteed that integrity and authenticity of the software. So for example, the Adobe is assigned the readers. So we know that Adobe signed the readers, and then integrity, and also is guaranteed integrity. So we know that software is never altered after the sign.
Except that the operating systems, when they do those code signing checks, they are not doing that for you. They're just seeing that it actually has a valid chain, and they're not saying, "Oh, well, this thing you downloaded looks like Adobe, but it's signed by somebody else." They're not doing that. Try it out.
Essentially, they just show the name associated with the signature.
Oh, they do show it. So some of them show it.
It's unknown publisher.
Yeah.
Doesn't chain properly.
If it doesn't chain properly, but it doesn't tell you, even if it's a known publisher. I mean, so I could sign something that looks like Adobe.
No, you cannot.
Yes, I could.
Something that looks like it.
There's something that looks like Adobe, and it would download, install, and have a valid signature going back to a root. It just wouldn't be Adobe's. And somebody who goes and checks to see who signed it would do that. But the operating system isn't doing that. It's just checking that I'm a valid developer.
So we'll take this.
Oh, sorry.
Yeah.
Okay, that was actually one of my questions, but I'll just ask one. So I work for 1Password, and we do not publish these checksums. I mean, we do. They're hidden. You have to ask and find out how to get them. But our experience is that the people who want to actually check them and are worried that we don't look secure because we don't have them are hard to convince that the fact that we have stronger code signing stuff and that we're actually downloading the binary also over TLS. So I think that there's a bit of a kind of a cargo cult in belief. So of those people who know about the checksums and want to check them, I think they may be overvaluing the security that they provide. And I'm wondering if you've seen that.
What do you mean I've seen that? So what's the question about?
Do the few people who actually care about checksums that you have found, do they understand do they understand that other mechanisms, such as actually getting the major download over TLS, pretty much solve the problem that they were trying to solve with the checksum?
I didn't ask him that.
Okay, yeah.
So we have time for one more question.
Okay. Yeah, first of all, I have to admit I'm one of those persons who never ever checks the checksum, so you already got me there. My question is, you showed the table where you saw that, or where we saw that instructions really exist. Do they exist, first of all, for all kinds of OS, so Microsoft, Apple, and Linux, or there's only one one OS system? And the follow-up question is, are these instructions really useful right now? Is it like the Windows instruction is an instruction which is longer than the actual download for the software at all?
So I cannot tell you for each of the software.
Yeah,
obviously but I think it was, well, it really depends. What I can tell you is that for OpenTGP and Ubuntu, it was quite clear actually. They really made an effort to make it understandable by everyone. But for the tools they used, I think it was always like giving instruction on how to do it in the terminal, which let's be honest, like roots out 99% of the visitors.
Yeah.
But yeah, that's what we observed. But it was more. It was always from the terminal, but on all systems, be it like Linux, macOS, or Windows, there is like a terminal command that allows you to compute the checksums, at least for SHA-256.
Okay.
Yeah.
Let's thank the speaker.